Hi class, welcome to 12.5 Adding Probabilities. Today we're going to take a look at finding the probability of mutually exclusive events and finding the probability of inclusive events. New vocabulary includes simple event, compound event, mutually exclusive, and inclusive events. Alright, let's start off talking about mutually exclusive events. If you roll a die, an event such as rolling 1 is what we call a simple event because it cannot be broken down into smaller events. An event that can be broken down is what we call a compound event. So for example, the event of rolling an odd number or a number greater than 5 would be a compound event because it can consist of a rolling a 1, a 3, a 5, or a 6. If there's two events, it's important to determine whether or not one event affects the second. Can they occur at the same time? So suppose I draw a card from a deck of cards. I want to know what's the probability of drawing a 2 or an ace. Since one card cannot be a 2 and an ace at the same exact time, this is what we call mutually exclusive events. Again, mutually exclusive events are two events that cannot occur at the same time. There's no way to pick one card and have that card be both a 2 and an ace. With mutually exclusive events, the way we calculate the probability is we simply find the probability of A and we find the probability of B, and we add those two things together. So that means the probability of event A or event B occurring is probability of A plus probability of B. So for example, Sylvia has a stack of playing cards consisting of 10 hearts, 8 spades, and 7 clubs. If she selects a card at random, what is the probability that it is a heart or a club? Now, if she's picking one card, there is no way that one card can be both a heart and a club at the same time. That's what makes this mutually exclusive. So the way we find out the probability of this occurring is we'll find the probability of each event taking place. So let's start with the heart. I know there are 10 hearts in this deck that she has, and there are 10, 18, 25 total cards. So the probability of drawing a heart are 10 out of 25. The probability of drawing a club would be 7 clubs out of 25 total cards. Now I want one or the other to occur, so what happens is I take my 10 over 25 for a heart, I take my 7 over 25 for a club, I add those two numbers together, and that gives me a probability of 17 out of 25. That is the chances of drawing a heart or a club out of a 25 card deck. Now remember, every probability we can look at as a decimal, 0.68, or as a percentage, 68%. That would be mutually exclusive events. Let's try another one, a little bit harder this time. The film club makes a list of 9 comedies and 5 adventure movies they want to see. They plan to select 4 titles at random to show this semester. What's the probability that at least 2 of the films they select are comedies? Keyword here is this "at least." Because they say "at least," that means it could be 2 comedies, it could be 3 comedies, or it could be 4 comedies. So what we have to do is we have to look at each given situation. So let's start off by looking at 2 comedies. If we're going to get 2 comedies, the probability of this happening, we first have to figure out what's the probability of, or how many different combinations we can have of all of these movies together. So first off, we have 9 comedies and we have 5 adventures, which gives us a total of 14 different movies we can choose from. We're selecting 4 of these titles. Now, because they are not talking about a particular order they have to be watched in, this is a combination. So I'm going to take 14 movies. I'm going to choose 4 of them. This here represents the total number of movies that can be viewed during this semester. So that's the total number of outcomes that we're looking for. Now, we want to find out the total number of successes. Well, first off, I want 2 comedies. So if I'm watching 2 comedies, that means I have 9 total comedies that I'm choosing 2. Now, this isn't quite enough, because what about the other movies? They make a difference too. Remember, I'm choosing 4. So because of that, I have to factor in those other 2. So I have 5 adventure movies, and from those 5 adventure movies, we're going to choose 2. Fundamental counting principle tells me, let's multiply them together. So there's the number of 2 comedies that could take place. Now, because that word "at least" is there, that means I can also potentially have 3 comedies in one semester. So to calculate 3 comedies, we again first figure out the total number we could have, which is the 14C4. 14 total movies, I'm choosing 4. And now I want 3 comedies. So I have 9 total comedies, choosing 1, order does not matter. Or sorry, choosing 3, order does not matter. And I have 5 total adventure movies, and I'm choosing 1. Multiply those together. There's a number for 3 comedies. Now again, because of that "at least," I have one more situation. And that situation would be, what if I have 4 particular comedies in this semester? 4 comedies in this semester. I start on the bottom. There are 14 total movies. I am choosing 4 of them. There's 9 different comedies, and of those 9 comedies, I want all 4 of them. Which means, of the 5 adventure movies I was having, I now want 0. Because these events are all mutually exclusive, meaning I cannot watch 2 comedies at the same time I'm watching 3 comedies. It doesn't work that way. It's either 2 or 3 or 4. I take each of these probabilities and we add them up. So let's see what we end up with here. We have 9 combination 2 times 5 combination 2 divided by 14 combination 4 plus 9 combination 3 times 5 combination 1 divided by 14 combination 4 plus one more set here, 9 combination 4 times 5 combination 0 divided by 14 combination 4. That gives me an answer of 0.905. Let's see if we can make this a fraction. Or 906 over 1001. Or just about 91% chance that we are going to watch at least 2 comedies in this given semester. Now, that's about as tough as they get. That included a little bit of everything, a little bit of combinations along with probability, along with the mutually exclusive events, so they don't get much harder than this. Let's try another one of those just to see see how things are going, make sure we're good here. The book club makes a list of 9 mysteries and 3 romance books they want to read. They plan to select 3 titles at random to read this semester. What's the probability that at least 2 of the books they select are romances? Now again, the key word, at least. So that means it could be 2, but it could also be 3. So let's start with the 2 romances. For 2 romances, we first need to figure out the total number of outcomes I can have. Order does not matter, so this is definitely a combination. I have 9 mysteries, 3 romances, which means 12 total books, and I'm selecting 3 of those books. So if I start with the romances, if there's 2 romances, that means I am choosing 2 out of a total of 3. That means out of the 9 mysteries that are left, I am choosing 1. For 3 romances, we again are going to take the total number of books, choose 3 for the total number of outcomes, and I now want to choose 3 romances from 3 books that I have, which leaves 0 choices for the 9 mysteries that I have. Because I can't read 2 romances at the same time I'm reading 3 romances in one semester, these are mutually exclusive events, which means let's add them together. So if we pull out our calculators, we have a 3 combination 2 times 9 combination 1 divided by 12 combination 3 plus 3 combination 3 times 9 combination 0 divided by 12 combination 3. 0.12, or about 12.7%. Let's see if we can get this as a fraction. 7 out of 55. So given 9 mysteries and 3 romance books, the probability of reading at least 2 romances in a semester are a little below 13%, or 7 out of 55. The second part of this lesson deals with inclusive events. The main difference between mutually exclusive, what we just finished, and the inclusive event is this. Suppose we're drawing a card from a deck of cards. I want to know what's the probability that that particular card that I pick is a king or a spade. That one card could be both a king and a spade at the same time. That's what we call an inclusive event. The mutually exclusive events were events that can never occur at the same time. So that was the 2 or the ace. There's no way a card could be both a 2 and an ace. However, a king could be a spade. That's what makes it an inclusive event. To figure out the probability of an inclusive event, we simply take the probability of event A occurring plus the probability of event B occurring minus the probability of both of them occurring together. So for instance, I would figure out the probability of picking a king, I would figure out the probability of picking a spade, and I would subtract the probability of picking a spade that is a king. So for example, let's say there are 2,400 subscribers to an internet service provider. Of these, 1,200 own brand A, 500 own brand B, and 100 own both A and B. What's the probability that a subscriber selected at random owns either brand A or B? Because a subscriber could possibly own both in this scenario, this is what makes it an inclusive event. So to figure this out, I start by finding brand A. The probability of brand A would be the total number, 2400, on the bottom, and the total number of brand A on the top, 1200. Brand B would be the total number on the bottom and the total number who own brand B on the top. If I add those two numbers together, that will give me the probability of brand A plus brand B, each of them occurring. But now, since they are inclusive events, I now have to subtract out the probability of someone who has both occurring. So again, there's 24 total 100 subscribers. 100 of these people own both. So to figure out the probability of brand A or brand B occurring, where it could be repeated, so it could appear both, would simply be, let's clear this out, 1200 over 2400, which, by the way, if you want to reduce to 1/2, you can, plus 500 over 2400, 2400 minus 100 over 2400, which gives us a total of 0.6 repeating, or 66.7%, or as a fraction, 2 over 3. So the probability of someone owning either brand A or B is 2/3. One more here. Let's say there are 200 students taking calculus next year, 500 students taking Spanish, and 100 taking both. If there's 1,000 students in the school, I want to know what's the probability that a student selected at random is taking either calculus or Spanish. Because a student can be taking both calculus and Spanish at the same time, this is an inclusive event. So we'll start off with the calculus. We'll say 1,000 students, and of those 1,200 are taking calculus. Probability of Spanish, we would say 1,000 students, and of those 1,000, 500 are taking Spanish. So the probability of calculus plus the probability of Spanish minus their overlap. Out of 1,000 students, the overlap is 100. And if we add all these together, you're going to see this adds to 700 minus 100, 600 over 1,000 students, which is 3/5, or 0.6, or 60%. So the probability at the school of a student taking either calculus or Spanish, if a student's chosen at random, is about 60%. They will have calculus or Spanish or both. I have some problems for you to try here. Some different scenarios. Figure out the probability of each one down here below. Some are exclusive, mutually exclusive, some are inclusive. You have to make the decision. But as always, answers are in red next to the question. Bring your questions to class, and we'll see you tomorrow.